All right, so in the previous videos, we talked about the basics of a titration, what is it, a quick review, and we also focused on some of the different instrumentation and the way that it looks, and the basics of the pieces and parts that make this piece of equipment work. So a burette chamber is going to be located on the majority of them, and then a touch screen that we can go in and key in information about our samples, and then some type of pH probe and a stir bar and a magnetic stir off to the side. So now we need to focus on the lab procedure. Like, what are we actually going to be responsible to do in this lab procedure? And I hope that it's not going to be a lot, and I hope there's no calculations, and I hope there's no spreadsheets. If you're saying that, I got kind of good news for you. There's very little of that because instrumentation does all of it for you. So this lab is going to be broken up into 3 parts. And the first part is the calibration of the pH probe. So just like when we use a pH meter in a lab setting, we're going to have to calibrate the probe before we use it and before we titrate anything at all. So that's why this is step number 1. And in order to calibrate a probe, we have to use 3 buffers most of the time. So those are buffers 4, 7, and 10. Now, you can use different buffers. You can use pH of 2, pH of 8, pH of 10. I mean, whatever floats your boat, use it. But 4, 7, and 10 is pretty standard. And when I say 4, 7, and 10, what this means is that this probe is only calibrated to perform extremely well between the values of 4 and 10. So if you're trying to measure a pH that's less than 4 or a pH that's greater than 10, then this set of buffers is probably not appropriate. You really have to ensure that your calibration encompasses the pH values that you want to focus on. And in this particular experiment and in the titration graph, the equivalence point is going to happen around pH of 6, 7, or 8. And because of that, a traditional set of 4, 7, and 10 is going to work extremely well for us. Now, keep in mind, you are more than welcome to change those buffers as needed, depending on what you're doing, but 4, 7, and 10 is pretty standard. All right. We never want a 1-point calibration, and that's because 1-point calibrations don't mean anything, right? We are pretending that that one solution is correct, and that one solution is exactly what that one solution needs to be. And if that one solution is off in any form or fashion, we have calibrated an entire probe based on that one thing and one thing alone. And it just doesn't quite make sense. Analytical wise, this is not what we're after. 1-point calibrations are common, but they are common with what I would call non-scientific probes. So if you have like a play pH probe, or you got a probe that you really don't care if you're just close, like this is pH of 4.7, but you know, if it tells me 6, I'm okay with it, then 1-point calibration is going to be okay for you. So we try to stay away from these. We do not like these. Anytime you see 1-point calibration, it's phony. There really isn't such thing as a 1-point calibration, right? You are basing your probe around one solution, and there could be many problems with that one solution if you're not very careful. Next up, you got an option of a 2-point calibration, and we don't like 2-point calibrations either. And the reason is because when this makes a regression line, okay, and meaning that when I go and plot, because that's how exactly this calibration piece is going to work. So when this system makes a calibration curve, it's going to say, oh, okay, I've got a pH of 4, I've got a pH of 7, and I've got a pH of 10. And what I'm going to see is a straight line that gets plotted onto a graph. So this straight line needs to be a straight line. And if I only pick 2 buffers out of the system, any 2 points make a straight line. So yeah, 2-point buffers are better than 1-point buffer. But 2 points are still not ideal because any 2 points make a straight line. and you are still assuming that those two solutions are completely perfect. There's no problems with them. They are fresh. They are made correctly. There's no kind of weird things that happen when you measured them, because you're measuring kind of the millivolts that's getting generated from these buffers onto your pH probe. That's how those work. So with that said, we have to do better. We have to make sure that 2 points are really getting self-checked. And to do that, we will at least use 3 buffers, so that way that third buffer can give us a better story. That third buffer can ensure that these 2 buffers make a straight line, and that one is not weird like the other one is. So for instance, if we did a 3-point buffer, and we did a pH of 4, and let's say that we did a pH of 7 and a pH of 10. And the reason that I'm drawing the calibration curve kind of backward is because that's exactly how the readouts are going to be. So when I place the pH buffer in 7, 7 has a reading of 0 millivolts, all right? So 0 millivolts, that's going to be the reading of pH of 7. And here on the graph, I've marked the 0, and we can go above, positive, and we can go below, and that's negative. If I put the pH probe in buffer of 4, what will happen is that this will often be like 180 millivolts, give or take a little bit. And that 180 millivolts will be a positive value at pH of 4. So this is pH of 7. And then negative 180 is going to be a pH of 10. So here, let me put 10 out here. So these are my 3 buffers. This is what kind of should happen when I begin to calibrate the probe, and to make sure the probe is kind of reading and functioning the proper way. That's the whole purpose of calibration. And if I make a straight line, then I hope that these 3 dots make a straight line, and I will get a y equals mx plus b. All right, what will happen is that the m value is the slope, and the slope, we know what that value should be. And that slope in actual, because this is what I actually did, because I actually ran it and did an actual calibration curve, will be compared to the theoretical slope. And that theory slope and the actual slope will be calculated and will pop out a number that's called a slope percent. And a slope percent is kind of like accuracy of the pH probe. So what happens very often is that we will take an actual and we divide it by the theoretical and we multiply by 100. So this will let us know, is it 95% good? Is it 100% good? Is it 97% good? And that's the kind of thing that we're after here. So the closer these 2 numbers are, we have less error. And if we have less error, then that means it's reading what it should be reading over the course of the calibration. So if there was only a 2-point calibration, what could happen is that, let's say that my 7 wasn't used. Let's say that my 7 wasn't ran, and my 10 actually gave me a point like up here instead of where it needs to be. Well, I don't have a third point to go by. So what would happen is that this would significantly skew my numbers, because my graph would somewhat do, if I could draw a straight line. What is wrong with me? I promise I'm not drunk. So what would happen is that number would be skewed off from the rest, and I would not know any different, but there's a chance that my pH buffer is wrong, because maybe it's not shelf stable. Maybe it's going to give me a weird number over the course of time. And that's very, very, very common, especially with pH buffer of 10. So I would not know this, and I would not catch it if it wasn't for a 3-point calibration, because a 3-point will help me keep myself in line to make sure it's reading the best way possible. So 3 is better than 2, and 2 is better than 1. What we are after most of the time is something greater than 95%. So when I complete the calibration curve, what will happen is that this probe will send a signal to the meter. the meter will calculate the slope percent, and that slope percent will be displayed on the computer screen, and it will be a value that I can take away from the calibration curve. If my value is lower than 95, then that means that this probe is not ideal. I probably need to recalibrate. I probably need to first, if I was going to do anything, just put fresh buffer on the probe and do the recalibration again and see what I get. And then if fresh buffer doesn't work, then I'm going to kind of monitor this on each buffer, because I know what each buffer should read in terms of millivolts. So if I put the probe into the buffer one by one and just measure it, I'll be able to see the response from the probe in that buffer to see if any one of the three is a problem. Because if I can fix that one that keeps triggering an error, then I can replace that one and maybe get a much better number here on the end. So there's a couple of ways that we can fix slope percents that are very low, and that's two of the easiest ways that we can do that. Next up, when I use the pH probe, there's going to be a plastic plug up here at the very top, and I want to make sure that this is unplugged, because this is like your finger on top of a straw that's filled with liquid. It will never drain. And what I want is that internal solution to somewhat drain out of these small porous holes that are at the bottom of this pH probe. If that is plugged, it will never drain. If it never drains, it doesn't interact with your solutions the proper way. And because of that, you don't generate the proper pH values the proper way. So by unplugging it, what you'll do is that you allow the interaction to take place. And now, because they're interacting the proper way, you're going to get a much better number as the end result. So that's what we're after. Please don't forget to unplug it. But then at the same time, when you get done with the pH probe for the day and your experiment is over, make sure that you plug that hole back. Because what will happen is that this will constantly drain the filling solution. And that filling solution will have to be replenished if you're not very careful and you forget about it and you just let it dangle. With that hole that's opened, it will continuously drip, 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 and you're going to ruin the probe if you're not very careful. All right. That filling solution is very often a 3 molar solution or molarity solution of potassium chloride. So it's just a simple salt solution, but we don't really want to do it ourselves. And that's because it really does need to be standardized, and we want to make sure we're using the correct concentration. And the problem with these pre-made reagents is they're cha-ching, cha-ching, cha-ching. They are lots and lots of money. So if you got money to splurge and spend, go ahead and order your little bitty bottle of 3 molarity potassium chloride and pay $100 for it. So, hey, if you're not worried about the pocket change, it's not a big deal. Let's just leave these probes out and open and unplugged all day, every day. And you'll be the favorite of the workplace. All right, so that's the thing with part 1 of this lab procedure. We're going to calibrate a probe. We're going to make sure it's plugged after we get finished using it. And we're going to make sure it's unplugged when we use it. And we're going to do 3 buffer calibrations, not a 2, not a 1. And those buffers will be 4, 7, and 10. So very simple process to calibrate a pH probe on our eco titrators. It is meant to be a very simple method. You really don't have to think too much at all. You just need to know, what button do I push? And that's really it. And that's kind of part of the lab activity and the purpose of it. So on the touch screen, this is what you're going to see. And when you go in for a pH calibration, what you want to do is down here at the very bottom, you're going to see a line item that will have an arrow, and this is your method selection, meaning that anything the titrator can do will be stored under a data file that's here. And I want you to think of this like a Microsoft Word or Microsoft Excel. You have created a document. That document is your method, and you've saved that document so that way you can open it up at a later date and look at it one more time and have the machine remember what your settings are supposed to be and how to do the proper calculations for those particular methods that you picked. That's the purpose of that very bottom line item. So what will happen is that on our titrators, you will click that arrow and there will be a method that will say something like pH calibration or something similar. pH calibration's too long, I believe, for that method name. They want you to abbreviate these method names as much as possible. You can only have a certain amount of characters that you can use, but either way, it will be very obvious which one that you should pick for the calibration portion of this lab procedure. So when you pick pH calibration, it's going to prompt. It will show up here in the line item after you select it, and then you will hit the play button that's down at the very bottom of the touchscreen panel. So if I go back and take a look at the Eco Titrator, right here is our play button. Ta-da! Right there. So you're going to hit it, and then it's going to say, put on your buffer. And then you put your buffer on, and you hit enter or play again, and it will measure that buffer, and it will give you the millivolts. And when it gets finished, it will say, clean the electrode, submit it down into your next buffer, and then hit enter or play again. So just follow the directions on the screen, clean it first, and then lower it into your second buffer, then hit the button that it tells you to hit. You never have to key in buffer of 4, buffer of 7, or buffer of 10. It knows what it should be based on the millivolt that it's reading from that solution that you have put on to that probe. And then after it gets finished with the second, it's going to say, raise the probe, clean the probe, put it into your next buffer, and then hit enter. Okay, so when it's finished, you accept it, and then you clean it off, you put it into the next buffer, and then you hit enter or whatever button it tells you on the screen, and then it will finish out that third buffer, and then it will automatically calculate the slope, ta-da, percent that you should be getting from the probe or what it saw from the probe. And hopefully, cross our fingers, it's 95% or greater. If it's not 95% or greater, you need to get me or someone else in the lab that's helping you out to figure out maybe what's going on with the probe, because we really like for that problem to be fixed before you go any further. All right, so that's the touch screen, or what a touch screen home screen will look like, and you will choose the pH calibration at the very bottom line, because that is your method selector area that you will go in and tell the machine, this is what I want you to do. All right, so that's part one. That is the calibration of the probe. And in part two, what will happen is that that instrument will have a titrant that is already loaded on the inside. And that titrant for this particular lab experiment is probably going to be sodium hydroxide. So this sodium hydroxide solution, it has been prepared by someone else, right? I mean, you didn't do that, we did it. And we've loaded it onto the machine. You don't know when we loaded it on there. We could have done it at the beginning of the semester or midway through. Who knows? So it's our job before we use that titrant, whatever that titrant is, whether it's NaOH or whether it's something else, it doesn't matter. We always have to standardize the titrant to make sure that the concentration has not changed over time. So the purpose of the standardization is to get the actual concentration that was prepared and that we're getting ready to use. So for instance, if I go into the lab and I make NaOH and I measure it out and I measure exactly the amount that it tells me to measure out and dissolve that in water and make a solution, folks, I still have to standardize. And the reason is because I am not certain that the exact measurement was transferred from my weigh boat into the container. I am not sure that the entirety of those grams fully dissolved the proper way before I put them into the solution or before I put them into the titrant bottle, right? I'm not certain that the NaOH, if this is what I had to make, was actually 100% pure. I mean, there was a powder there or pellets, and I was weighing that stuff out. Was it 100% pure, or was it 99% pure, or was it 95% pure? I don't know. I'm taking risk and I'm taking gambles, and that is the reason that we have to standardize every single time we make a titrant, no matter what that titrant is. So I'm going to standardize when I make it, because that helps me determine what the actual value is from this point forward. And then number two, I'm also going to standardize it at least daily. So every day, if I go into the lab and my job is to titrate for the day, I'm going to make sure that that titrant has been standardized in the morning at least. Before I use it for anything at all, I'm going to run a standardization method. Most of the time, these standardization methods are ran 3 times, and I do an average. And that average is the concentration that I will key into the system from this point forward for the rest of the day, maybe, until I come back in tomorrow to do more titrations on a different date, or maybe different samples. There are times that standardization will happen in the morning, and then it will also happen midday. So I'll come in at 8 o'clock in the morning, I calibrate the probe, and then I standardize. I run 3 trials and I do an average. And then midway through, maybe at a shift change for the evening folk that come in, that pick up from where I left off, they will go through a calibration again, and then they will go through a standardization again. And they will generate 3 data points, and they will do an average, and they will key in what their average is for their shift when they do the samples from that moment on. It just really depends on how the company is actually set up to run. So, what do we standardize with? Well, for sodium hydroxide, one of the most common is something called potassium hydrogen phthalate, which is abbreviated as K for potassium, hydrogen H, and phthalate P. So potassium hydrogen phthalate is a compound that you're seeing over here on the right-hand side of the screen. And potassium hydrogen phthalate is an acid. So here's the trick. We are using sodium hydroxide in our burette. Sodium hydroxide is a base. We want to know, what is the concentration of the base? If I'm trying to figure out the concentration of the base, I need something to react with it. So I need an acid to react with it. If I use another base, none of this makes any sense, because you can't titrate a base with a base, because no reaction really sometimes is going to happen between the two. So they always have to be opposites. That also means that if it was hydrochloric acid that had to be standardized, okay, well, if hydrochloric acid is going to be standardized, I probably shouldn't use another acid to standardize against it. I need to use a base to standardize against it. So I would choose something different other than potassium hydrogen phthalate. I would choose a different compound that the method will tell me to use. So KHP is pretty common. It's also very cheap. It's one of the reasons that it's often used, because price point, it is not expensive at all. And it's something that we call a primary standard, because this is a solid, not a liquid. And that makes this even better. And the reason is because if they were liquids, you could have problems with evaporation. So I want you to think of making a solution and dissolving stuff in that solution, and that liquid, even if it's water that you've dissolved it in, could evaporate over time if you're not very careful, right? It's like a swimming pool outside, a little kiddie swimming pool outside on a hot summer day. Your volume in total is going to change. The longer it sits, the hotter the room's going to be. You're going to get some evaporation that takes place. You're going to lose some volume, and that changes your concentration. So we never like that when that begins to happen, especially if we're using it in the standardization process. So what happens is that a solid can actually be measured out in terms of gram, and that solid, we don't have to worry about volume changing, because it is a solid that we're measuring out onto a balance. At the same time, this particular solid doesn't really reach out and grab water too much. It's not notoriously known to be hydroscopic, so it's not going to grab water and turn into a liquid as it sits in your weigh boat. So very friendly, very stable, and very cheap. And that's why KHP is often used to standardize sodium hydroxide. Keep in mind, though, there are many different versions of primary standards here. Depending on what you're trying to titrate with, that has to be standardized. There are primary standards that go along and work extremely well with those particular solutions. So you will change that KHP up over the course of time, but for this lab experiment, that's what you're going to be using. What makes this thing an acid? If I look over here to the right-hand side and I begin to kind of scrutinize this particular type of structure, a acid is a proton donor, right? So I'm looking for protons, and there are hydrogens that's on this molecule that's not drawn, but one hydrogen in particular is very important, and that is, ta-da, the one in red. That is our acidic proton. That is the proton that will be spit out when this molecule behaves as an acid. This functional group that hydrogen is on, this is called a carboxylic acid. And that carboxylic acid, that name tells you everything you need to know. It is an acid, which means it's a proton donor, which means it spits proton off. So these are acidic pieces of a molecule when they form. And that carboxylic acid, folks, this here is a carbon. It's not drawn, but it's understood to be a carbon. So that carbon, double bond O, connect it to an OH. That is a carboxylic acid functional group right there. So that carboxylic acid is what makes this an acid, which what makes this appropriate to be a acidic primary standard to titrate sodium hydroxide against. All right. The C double bond O, that also has a name. That is actually called a carbonyl, C-A-R-B-O-N-Y-L. Carbonyl. So that is a B. That carbonyl group, there are many different versions of carbonyls. Carboxylic acid is just one of them. So think of carbonyl as an umbrella term. And those carbonyls can give rise to many different functional groups in the world of chemistry. And those carbonyls, one of those options that it can make is a carboxylic acid. So if it has an OH attached to the carbonyl piece, then this is called a carboxylic acid. And there's a few properties that it brings to the table. All right. So in the part 2 of the lab experiment, you're going to measure anywhere between 0.2 to 0.3 grams of KHP, and you're going to do that on a balance. You're going to make sure that these are completely dissolved. That's actually going to take a little bit of time, so don't just automatically titrate these. Put a magnet in them, stir them, get them ready for your titrator, and make sure that those crystals are fully dissolved when you measure those out. All right. The instrument is going to take your gram that you have measured, and you're going to have to key that in. So when you begin this method, you are going to go over to the touch screen. You are once again going to go to the home screen, which is this. And down here at the bottom, this is your method list. You're going to click the arrow just like you did before. And this time you're going to choose NaOH standard, or something like that. Again, it's limited characters. That's what it displays, but it kind of makes common sense. That's what you want. So standardization of NaOH. So when you choose that method, you're then going to go back to the instrument. You hit play. So in the corner, you hit the play button, and then it's going to ask you to key in the gram of KHP that you've measured out with this sample. So make sure that you write down those numbers. Make sure that you keep them organized, keep them ordered so you know which gram is in which beaker. And that number is very important because you'll have to key it in to the system when you put it on there. All right. So the instrument is going to take the gram of KHP and it's going to divide by 204.22. And the reason is because that's the formula weight of KHP. And that will be the moles of KHP that you have in your beaker. It's going to take the sodium hydroxide and it's going to use that drip, 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 drip until all of the NaOH or the KHP is now neutralized and taken care of. When that happens, the titrator knows to stop. So the moles of KHP will equal to the moles of NaOH that was required to kill it out. And then it also knows the milliliters of NaOH that it took in order to get to that point. So it's going to take the moles of NaOH and it's going to divide by the liter of NaOH from the burette, and that will give you molarity. And that molarity will be popped out onto the computer screen. So once again, no calculations. Woohoo! And then what will happen is that you'll repeat that 2 more times, but the calculation you will have to do is an average. So it will tell you the molarity on the screen, and that molarity you will have 3 of. Do a quick average using a calculator, add all 3, divide by 3, and then we need to key that value into the system once we begin to titrate our samples, or before we titrate our samples. I also want to mention that no indicator is needed here, and the reason is because this instrument does not work visually through an indicator. This equipment works with equivalent point. That is what it has been built to do, and that's what we take advantage of. So therefore, no preparation of an indicator is going to be needed. No addition of an indicator is going to be needed. This acid-base titrator will look for equivalence points, and wherever that equivalence point happens, that is where the instrument is going to stop, and that is how it bases its calculations. So again, much easier, less sample prep, and I don't really have to figure out which indicator is going to be the best for my method, because I don't really need one to begin with, and this machine is much better than my eyeballs because of that. Once you determine the average, you need to key that into the titrator system. So again, here is the home screen, and that home screen is going to be the area that we're going to go into in order to key in the concentration that I have calculated for an average. All right, so we need to go in there and we need to kind of figure out how do we do this. There's a couple of different buttons here that I'll talk about eventually, but for now I'm going to stop the video here. In the next video we'll pick up from this and we'll talk about what needs to happen next as far as me getting that titrant concentration into the system. And with that said, I gave you a magic little keyword that you probably are like, oh, well, that's probably where we do it. Well, we'll talk about that in the next video.